Hello guys, in this video we shall be talking about the last topic of PH108, which is electromagnetic waves and Poynting vector. So let's begin. So we have derived or at least gotten the complete set of Maxwell's equations, which is the divergence of the electric field being equal to rho divided by epsilon naught, the curl of the electric field being equal to minus the partial derivative of the magnetic field, the divergence of the magnetic field being equal to 0, and the curl of the magnetic field, which is the Maxwell-Ampere law, being equal to mu naught j vector plus epsilon naught del E by del T. So since we have the complete set, we can go further. So the next topic is about electromagnetic waves. So in electromagnetic waves, what we are going to do is we are going to assume a source-free region where rho is 0 and j vector is also 0. So with that, we can actually get wave equations for the electric field and magnetic field. And with that, we can actually solve them using certain tricks, and we can actually get expressions for them which show or guarantee the existence of electromagnetic waves. So we can talk about the wave vector first, which shows the direction of motion, and it's represented by kx, ky, kz, which are the components along x cap, y cap, and z cap. And then we also can get the expression for the electric field and magnetic field, which would be E naught times cosine of k dot r minus omega t, and B naught times cosine of k dot r minus omega t. So these expressions are quite important. In addition, we can also get properties like all of them being mutually perpendicular and the propagation speed, which is c, which is equal to omega by the magnitude of the k vector, and that is equal to also square root of mu naught epsilon naught inverse. So it will be 1 divided by square root of mu naught epsilon naught. We can also get expressions for the energy density of the electric component as well as the magnetic field component, and we get them to be both equal. So that is interesting, and these properties are quite useful. Then the next topic is the work done by the electromagnetic force. So if we have a system of charges and currents, so what will be the work done by the electromagnetic force, which is Q V cross B plus E. So what will be the work done by that? So we can get an expression for the conservation of energy, which will state that the work done or the power instead, because we are going to take the derivative with respect to time. So the power in some sense will equal the rate of change of the electric field and the magnetic field energies with respect to time, plus some loss due to radiation in some sense, which will be described further. So UE is the electric field energy, which will be the integral over the volume of the energy density, and the magnetic field energy will similarly be the integral over volume of the magnetic field energy density. Then this last component, which is quite important, is related to the Poynting vector, which represents the energy flux density of radiation. So S vector is E cross B divided by mu naught in this equation. So for EM waves, we can substitute E vector as E naught cos k dot r minus omega t, and B vector we know is k cap cross B E naught divided by C. So since we know these relations, we can actually get S vector in terms of E naught vector, mu naught C, and these other things which we know. And we can also find a time averaged version of this, which is the average value of the Poynting vector will be mod of E naught squared divided by 2 mu naught C times the k vector. So these were some of the important topics which are there in this section on electromagnetic waves. So that's all for this course. Almost all the topics have been covered, at least in basic. Details can be covered by referring books like Griffiths or other things, but all the topics have more or less been covered. So I hope you have stuck around and seen most of the topics and gotten a fair idea of what is there in this course. So thank you.